here I've had a pretty long career in the Navy. I've been in now almost 23 years since I was commissioned. So to give you a little bit of an idea of how broad nuclear engineering is, because of my eclectic background, I can tell you what I've been able to do with my nuclear engineering degree from undergraduate to today, to give you a perspective for what you can do if you were to get a degree in nuclear engineering. So I started off as an undergraduate nuclear engineering student at the University of Illinois, and I really wanted to go into nuclear fusion. That's a pretty common motivation for people to join nuclear engineering. And this was from 1992 to 1996. I was a naval ROTC student, so I didn't have to worry about getting a job right after undergraduate. I had that taken care of. I didn't have to worry about tuition. I didn't have to worry about doing all the ROTC things on the side, but, you know, trade-offs. And as I was going through my undergraduate major, first, I wound up finding out that I really, really like electromagnetism, which at Purdue is physics 241 or 272. And as it turned out, fortuitously, that's a very important part of fusion and plasma physics. And then as I moved farther on in undergraduate, I realized that I really liked the idea of doing research. Back then, we didn't do research for credit. It wasn't something that undergraduates typically did. It's something that's much more prevalent today, and being a small department, our students can be very actively involved. I typically have anywhere from 8 to 10 undergraduate students doing research for credit for me during a given semester, with numerous majors: chemical engineering, electrical engineering. I got my first agricultural and biological engineer this semester. So we're very multidisciplinary. But I never did research as an undergrad. But I did teach for the math department. I did do ROTC. I did get to go out on a nuclear submarine and see what that world was like. And based on all that, I took a 1.5-year leave of absence from the Navy to get a master's degree at the University of Michigan. And at that time, the fusion programs in the country were kind of challenged from a funding perspective. Funding is a big driver in research. It tends to go up and down. So the work that I did at Michigan as a master's student was more related to plasma physics. Specifically, it was related to what are called crossed field devices, like the magnetron in your microwave oven. That magnetron is what's called a crossed field device because the electric field and magnetic field are perpendicular. That may or may not mean anything to you at this point in time, but the important thing is that that was the technology that helped win World War II on the European side, because it provided the radar systems for the Allied forces against the Germans, okay? So it's important technology, but there are a lot of questions that remain to this day, because we're still funded to do that research, about how those devices work. So I did my master's degree, ironically funded by the Navy, even though it wasn't through a military program for me being in uniform. It's just the research was funded by the military. And I got my first master's degree and then went into the Navy. So the naval career, for those of you that might be interested in such a thing, I was a submarine officer. I went through about 1.5 years of training, about a year in Naval Nuclear Power School, and then prototype. So that was a total of about 12 months. 6 months classroom training, 6 months on what's called a moored training ship. Basically, it used to be a submarine, and they pulled it into port, and you actually operate the reactor to learn how to operate one when you get out to the ship. All right. Then I went to submarine officer basic course. That's that little sliver there that you can't really see in 1999. Spent 3 months there learning the basics about being a submarine officer. And then I was a submarine officer for 32 months on the USS Pasadena. And the letters there, I was reactor controls assistant. So I was in charge of the instrumentation and controls. And in that position, we pulled into the shipyard. We took out all of the electronics for measuring reactor power and reactor operations, and we replaced it. It was what's called analog. We replaced it with digital. And I wasn't still in that position when we replaced it, but I was in that position when we took it out. Then I was chemistry and radiological controls assistant. Our reactor power plants in the Navy are what are called pressurized water reactors, which means you've got water flowing in the reactor system and in the secondary system, which is basically a steam plant that provides the steam to turn the turbines to make power and to make the ship go. So I was in charge of making sure that water chemistry was correct, so you didn't corrode things. I was also in charge of making sure that when people went to do maintenance, that we managed the radiation exposure, make sure those people didn't exceed their dose limits. And that was a very important job towards the end of the shipyard period when we were starting to put everything back together. That leads into my third job, QAO, Quality Assurance Officer. I was in charge of making sure that after 18 months of making big holes in the ship and tearing things apart, that when we went back out to sea and went underwater, that we came up. And I did a great job because I'm here 18 years later to tell you about it. So clearly I succeeded. And then finally I was Communications Officer. That was the last about 6 or 7 months of my time on board. And that's what we called a forward job. That's more on the operations side, making sure that message traffic went between the ship and squadron, dealing with classified material, things like that. So I did that for 32 months, and I was ready to move on. I didn't really want to go back to sea. I will tell you that it was a great experience. I'm glad that I did it. It makes me a better professor because I have worked in very challenging environments with a vast array of people. And it's something my dad told me. My dad was career Navy as well, but he retired before I was born. But he was a career naval officer. And he told me that the experience you get in the Navy will set you up for life regardless of what you do. And I will say, from a leadership, management, being able to survive stress and challenges, working with different types of people, nothing compares to that 32 months that I spent as a submarine officer. So after that, I went to shore duty. Shore duty is, you can think of that as like the payback for the 32 months of sea duty. And I really, really wanted to get back into the graduate school thing and go into research. And at that point, I decided that I wanted to be a professor. And the Navy sent me to Norfolk, Virginia, where I was an instructor at submarine training facility. I basically taught the courses that we take as junior officers before we go to naval reactors, which is basically our version of the Nuclear Regulatory Commission in the Navy, and made sure that the students, the junior officers, were ready to go become certified to be the chief engineer of a submarine. It's basically a certification we did at the end of that junior officer tour to make sure we could go back and be a department head, which is the next career aspiration. So the nice thing about that was it was really a 7:30 to 3:30 type of job. So I called my advisor at Michigan, and he geared me towards a faculty member at Old Dominion University, which was just down the street from the naval base, who was starting what is now called the Frank Reedy Research Center for Bioelectrics, which is taking all those concepts that we learn in nuclear engineering for fusion, which are pulse power and plasmas and lasers, and looking at those for biomedical applications. So I kind of stumbled into that sort of research because the Navy sent me to Norfolk, and the only person with funding to do research at that time was this professor. And I always kind of wanted to do biology too, but I didn't want to sit and memorize. It was too much memorization for me. I wanted to be something more mathematical. So what you see here is from that point where you have sub-TRAFAC and Old Dominion University here, you see two tracks. The top track is my military career. The bottom track is my civilian career. So I got a master's degree in electrical engineering from Old Dominion, and then I went back to the University of Michigan to get my PhD. Now, my choice of majors, going back to where you are now in your life, I was looking at 3 majors at Illinois. I was looking at electrical engineering, nuclear engineering, and engineering physics, okay? And I went back and forth about which one to major in. And there was one thing with each major. With electrical engineering, I really didn't want to do the computer engineering stuff. And it was just a little bit too practical for what I wanted to do. It was too much circuits and that sort of thing. So I didn't really want to major in electrical engineering. On the other end, I really wanted to be an engineer. So engineering physics got a little bit too esoteric. There's a little bit too much physics in that. I chose to major in nuclear engineering because I could make it the best of both worlds. In nuclear engineering, I took similar types of classes to the physics majors, but they were all in engineering. You take thermodynamics, you take basic materials, you take, obviously, the basic physics courses, because everyone takes those, but we take nuclear physics. And basically, I took a lot of the same classes that a physics major would take, but they were in engineering. And I was able to strengthen that because at Illinois, in particular, I had to take 15 or 18 credits of technical electives. So I took all my electives in things related to electromagnetism, which was related to fusion, and which was related to motors and generators, because motors and generators are very important in the Navy for actually generating the power. That's a large chunk of what you cover in nuclear power school. People think it's all about the nuclear reactor. A large chunk of it is actually the electrical engineering, because the whole point of having the reactor is to generate heat to boil the water to move stuff. Okay, well, you don't boil the water, but you heat the water to make steam. Okay, so that was how I wound up in nuclear engineering. Obviously, my interests have some sort of alignment with electrical engineering, but I'm certainly more closely aligned with the nuclear side. So for my PhD, I did work on the bioelectric type stuff. I actually did interesting projects. I modeled the growth of a tumor. I modeled cell population dynamics. And then I continued my naval career. My first tour in parallel with graduate school was working for a submarine squadron. And I did some really cool exercises out of Naples and out of Northwood, which is near London. However, in my opinion, that career path was somewhat boring. It's important work. I mean, you have to make sure submarines don't hit each other. Very important. But to me, it was kind of mind-numbing. It wasn't interesting. So when I got my PhD in 2006, my civilian career led me to GE Global Research Center, where my job title was loosely electromagnetic physicist. I did all sorts of projects, some of them bioelectrics related, which I continue to collaborate on with GE to this day. I did some RF type of things, basically microwave things. In fact, I just had a call with my final lab manager today looking at collaborations for a Department of Defense proposal. So I've been able to maintain these ties from this industrial work even 8 years after I left. Up top, my military side, I became what's called an engineering duty officer in the Navy. And engineering duty officers work for what's called Naval Sea Systems Command. Naval Sea Systems Command is the group within the Navy that basically makes the requirements for building new ships, purchasing weapons systems, doing all this stuff. They manage the shipyards. My career going up top here, I worked with Surge-Main Albany. Surge-Main's this big program. It's about 1,700 enlisted sailors with officers managing it. And they provide support to the public shipyards. In fact, they mobilized over 1,000 of these sailors just over the last couple of months because of COVID-19. The shipyards have fallen behind, so the Navy is using this surge capacity to send these enlisted sailors out to the shipyards to help make up for the lost production. And as we move along the top, my military career, I went from Surge-Main Albany to, which is where GE Global Research Center was, to Portsmouth Naval Shipyard, where I was the executive officer, second in command of the headquarters unit, became the commanding officer of that unit. Then I moved to a 2-year tour based out of Naval Research Lab and Naval Surface Warfare Center Dahlgren, where I worked on railgun modeling for a little over 2 years. Then I moved on to being what's called a regional commanding officer. So I was a regional commanding officer for 4 years, in charge of 8 to 10 reserve units, around 200 sailors for each region. And I would go around traveling on the weekends to visit my unit commanding officers and make sure they had everything that they needed. Okay. Meanwhile, at the bottom, I spent the 6 years at GE Global Research, joined Purdue in August of 2012, just got tenure and promotion last year. And I run a research group at Purdue that does research into intense electromagnetic radiation. Particularly, a lot of my research currently is Department of Defense funding. One of the biggest issues in the Department of Defense is what's called directed energy, using high-power microwaves to disrupt electrical systems, for instance, or for non-lethal defense, such as using these 94 gigahertz radiation to stun people, basically make them feel uncomfortable so that they don't try to attack, all right? So that's the DoD side. We're also funded right now to look at using pulsed magnetic fields for pain remediation. It's also funded by the Defense Health Agency, okay? From a commercial side, we're funded by Syngenta, which is a crop production company. You may have seen their signs when you travel around. this part of the country. But we're looking there at using low-intensity electric fields to modify biological cells. Basically looking at ways to do genetic modification without making it GMO, all right, electrical GMO, if you will. All right, so as you can tell from my parallel career paths, there are a lot of things you can do as a nuclear engineer. The reason for this, and the reason I stuck with nuclear engineering, is because you have that sort of breadth. Yes, you are the expert on radiation. We're the only major where radiation is something that is native to us, because we have to take those radiation courses and the radiation lab course as an undergraduate. So we get that experience that other majors don't have. But for instance, with my background, I had to take a lot of basic mechanical engineering courses, right? And I can't say I enjoyed them, I'll be honest. But I actually used that stuff at GE because the electrical engineers didn't understand that stuff. And I'm not talking really advanced, just at the level that I learned at undergrad, I was able to apply that to very important problems and provide useful outputs to guide the industrial functions. Okay, so that's my biggest pitch. My biggest thing is, do not be concerned that nuclear engineering will constrain you. Okay, you have a lot of opportunities, especially if you go to graduate school. I mean, you can do a lot of things as an undergrad too, but once you go to graduate school, no one cares what your major is. They care what you have done. And I can tell you this because I've had 2 recent PhD students that this has been true of. One of them got his undergraduate degree in mechanical engineering, did a master's degree at Purdue doing thermal hydraulics, which is fluid flow and heat transfer, okay? He got his PhD with me in nuclear engineering, looking at using electric fields to modify cells. He is now a postdoctoral scientist at one of the world-leading labs at Virginia Tech, where he's leveraging all this expertise, and he is doing very well there. I have another student who just defended in August. His research was looking at the effect of very small gaps and looking at how applying voltages affected the what's called breakdown or the formation of plasma. All right, it's very, very hardcore plasma oriented. But his degree, his PhD, is actually in agricultural and biological engineering. But he's going to be working with the High Power Microwaves Directorate at Naval Research Lab. So even though there's a little bit more paperwork, because they think it's weird that his degree was in ABE, it's not hindering him, okay? So at the end of the day, the degree is important, but if you get a degree in nuclear engineering from Purdue, you can go off and do very interesting things. The student I just talked about from ABE, his bachelor's and master's degrees were in nuclear engineering, okay? So that's my career. The reason I like to go through this, it may have bored you, but I want to just point out that there are many paths that you can go on with this degree. And as we've talked about, you're applying this nuclear physics for fission and fusion, non-proliferation, medical applications, particle accelerators, and propulsion. And I've touched on a lot of those as I've went along. And again, it's a diverse major. The mechanical engineering courses that we take, statics and dynamics, thermodynamics, even though they're in nuclear engineering, fluid mechanics, heat transfer, and the fluid mechanics and heat transfer lab. They're in nuclear engineering, but they're fundamental ME courses. Material science and material science lab, we have 2 3-credit courses. Radiation instrumentation, it's radiation instrumentation, but in essence, that's fundamental electronics. And then of course, nuclear physics. So the first 2 years are virtually identical to ME, except for taking the introductory nuclear engineering course in the first nuclear engineering lab, you're basically in ME. When I was in Illinois, my first 2.5 semesters, except for 1 course, I took exactly the same with the MEs, okay? After that point, you tend to become more diverse. And as I pointed out earlier from my experience, with the right technical electives, you can look like a EE or an MSE in a specific field. In my case, even though I'm a nuclear engineering major, I've taken more electromagnetism courses than many EEs because they specialize in different areas. So it provides you with unique breadth and depth for multidisciplinary knowledge, which is becoming increasingly important in industry, in government labs, in government jobs. It's increasingly important to be able to look at systems from a broader perspective. And nuclear engineering gives you that because we have to take everyone else's basic courses. you are well aligned to have that sort of fundamental broad knowledge. So what do our students do? Well, half go to industry. Obviously, I've talked about the type of courses our students take, so it shouldn't surprise you that the other half pursue advanced degrees and go work in laboratories, either government labs or industrial labs in universities. Average starting salary for BS is about $67,000. I just got this online last night. The average median salary is about $106K. Obviously, numbers will vary depending on particular jobs you take. And then what do these jobs look like? This is your broad perspective, okay? Obviously, you'll get the standard things, electricity. About 20% of power is usually nuclear power. You see all sorts of other things, consumer products, space missions, science research, agriculture, industry. Nuclear engineering touches on a lot of different areas. Power generation, obviously that's the one that everyone always thinks about first, well, most people. Nuclear power stations. There's a lot of interest right now in small modular reactors. I would argue the science for this is fairly well known, since a submarine is basically a portable small modular reactor. That being said, doing it on the commercial level and figuring out how to scale it is challenging. Also on the commercial side, getting the licensing. A lot of times the issues are not technical, they become more political. I get asked frequently about the future for students who want to go into nuclear power, all right? And the honest truth is, even if we don't build new power plants, right, the age demographics of the people who work here tends to skew higher. So we're going to need replacement workers for those workers. So even without building many new plants, there's always going to be a constant drumbeat for new employees in these fields. Obviously, my old home, naval nuclear power. All submarines in the U.S. Navy and all aircraft carriers are nuclear powered. Each carrier has 2 reactors. Each submarine has 1. There is an ongoing drumbeat constructing a new submarine every year. So there's always going to be new nuclear power plants built in the U.S. For the Navy. So career opportunities, one is you can pursue civilian career opportunities working for the Navy. I've had students with job offers to work at Bettis Labs in Pittsburgh, where they do the designs for the Navy. You can work at Knowles Atomic Power Plant or a power lab up in Niskayuna, New York, where I used to, right next to where I worked at GE. They do a lot of the design work there. There are programs to go in uniform to teach at Naval Nuclear Power School in Charleston, South Carolina, or to work at the prototypes. Both, I think they still have civilians. Back when I went through, there was contractors, but I think they now hire uniformed as well, where you can go in, get a commission as an ensign, and go work as an instructor at either place, okay? Then obviously there are the programs where you get a commission and become what's called an operator. So you become either a submarine officer like I was, or you become a surface worker officer and you go to a carrier and you get a surface worker officer pin and serve your 5-year commitment. I was commissioned through ROTC. So you see those students, some of you may be ROTC students yourselves. You'll see them going around on campus when we go back to campus eventually, once a week in uniform. There's also what's called the NUPOC program, Nuclear Propulsion Officer Candidate, where you don't wear a uniform, but you're paid as an enlisted member for 2 years before you get your degree. If you're in-state and interested in going into naval nuclear propulsion, it's generally a better deal to do NUPOC than ROTC. If you're out of state, ROTC is a better deal. Okay, plugging my research area, you've also got national security from the directed energy side, high power microwaves, high power lasers. Directed energy is one of the critical areas of technology development from the Secretary of Defense. And as such, a large chunk of my group right now is funded to look into directed energy. And we're working now, there's a lot of interest at the DoD level on the biological effects of these technologies. And I'm working on getting my research group more involved in those too, since we're uniquely positioned. That leads into medical. Obviously, isotope production, medical imaging technologies, radiation therapy, all these things are traditional nuclear type medical treatments making use of radiation or radioactive materials. My research group uses the intense electric field component from plasmas and fusion. So on the upper right, you'll see a system that we constructed, we being GE. We started this work when I was at GE and continued the collaboration since I came to Purdue. And we actually use that system to activate platelets. This is a technique used in both wound healing and in medical treatments. Particularly, you can imagine this for diabetic wound ulcers. And what you do is you draw the blood from the patient, spin it in a centrifuge to concentrate the platelets out. Okay, so it's just now a platelet-rich plasma. And then you put in this external agent, which is called bovine thrombin. And this bovine thrombin causes the platelets to release proteins. And these proteins are called growth factors that help heal the wound. Okay? The problem with this approach is that bovine thrombin, some patients have really bad immune responses and allergic reactions. And treating that can be very expensive, as well as the fact that the bovine thrombin itself can be very expensive. So what we're looking at is taking out the bovine thrombin and using a high voltage pulse generator. And we've worked on various things. We got several patents on this. In fact, GE has licensed the patent to a cosmetic company, which is doing some interesting work, not medical, but cosmetic work. And we're still working. We've got some clinicians who are interested in this, and we're hoping to be able to use this for more on the medical side, trying to do some animal studies to convince people of the utility of the approach. Then you've got food and agriculture, so you can use radiation to delay ripening, sterilize food. You probably heard of some of this with like milk and other things where people use radiation. Pest control and seed preserves. What my research group has collaborated with another group from food science is actually using the plasma shown on the left. So they're applying a very high voltage here into a bag. This bag here, that's a bowl, but it can be a bag. We've used bags and stuff too, a plastic bowl. But what you're doing is you're applying a voltage to this gas. You're breaking it down to form a plasma. That's this purple that you're seeing here. And that plasma is full of charged particles, and those charged particles break open the microorganisms and cause them to die. So here you're looking at some tomatoes a couple of weeks after treatment and not after treatment. So you see not after treatment, the microorganisms have survived and you don't want to eat those. But here, those tomatoes look good enough to eat. You can see some of the decomposition from the non-treated areas, like on the stem. But generally, these tomatoes look very fresh. So we've collaborated with food science on some things with plasmas, and we're hoping to continue that sort of work. Space. So many of you may have heard that there's now a new branch of the military, the Space Force. And part of that involves powering these spacecraft, right? So you can use radioisotope power, which is like a nuclear battery. I did a little bit of work on that when I was at GE. We were looking at using alpha particles, which are helium atoms without the electrons, right? And they're very heavy, very charged, and you use that to interact with materials to basically give off energy to power to your battery. Typical battery uses beta decay. Ion energy engines, this is very similar to what my research group does, looking at electron emission, trying to use that to propel your spacecraft. And then, of course, you're not complete without miscellaneous. So you can use radiation for gemstone coloration, materials manipulation, desalination, hydrogen production, plasmas for combustion, something my group has worked in. We've actually worked with some chemical engineering undergrads to use electric pulses to extract the lipids from algae. You can use those lipids for biofuel. So we've done that sort of work. We've also done work with electric pulses to activate stem cells and to inactivate microorganisms. So you can get rid of these antibiotic-resistant bacteria. So there are a lot of different things within the nuclear engineering umbrella that you can do. So what do you get out of this? Well, you're going to be a highly skilled engineer, similar to an ME, but with, depending on how you choose your technical electives, you can be more broad. Ability to solve complex systems problems. Again, to understand nuclear engineering, you have to understand bits and pieces of everyone else's major. So as the world becomes more and more highly multidisciplinary, that's a valuable skill set to have. Pathways, we don't have any official tracks anymore, but it's incumbent upon you as a student to determine what technical electives are interest to you. You can work with the faculty to determine that for your particular interests. There are various common minors: physics, math, global engineering, material science and engineering. I know the ROTC students can get minors in their respective sciences. We have had some double majors. The most recent one I'm aware of is aerospace and aeronautical engineering. The other thing that you can do is actually what I had planned to do, but didn't quite work out. I got my undergraduate in nuclear engineering and was thinking about getting a master's in electrical engineering. So if you take the appropriate classes, you can do things like that as well. 126 credits for graduation, and a minor is 12 credits. And if you have questions about either of those, feel free to reach out to Holly. With that, Tyler, are you online? Holly, were you able to get oh, you are there? Okay, great. Can you talk about some of the courses that you've taken that you found interesting?
Sure. So a few of the courses I found really interesting were your NE 205 class last semester. I really loved learning about radiation detection and sort of seeing all of that come together. Another favorite course of mine was actually NE 200, which was the introduction to nuclear physics course that Tally Arkin at least taught for me. And I really liked that course because it gave me a broad view, not very in-depth, but gave me a broad view of the nuclear physics side of things and how that relates to industry, how that all got started historically.
And Dr. Garner, I'm also on the line, so I can speak to some of the, so Tyler is a junior in nuclear engineering, I'm a senior in nuclear engineering, and I'm currently in NE 305, which is really fun. It's sort of it's the second undergraduate radiation lab that you get to take, so it sort of builds off of what you do in NE 205. And in that class, 205 is a lot of like detecting alphas and betas. Really, 305 is more focused on, at first, gammas, and then a lot of like neutron kind of detection and neutron science. You get to use the subcritical pile, which is sort of like a reactor that's not quite there yet. It doesn't have quite enough fuel to become critical. And then you also get to do some experiments with the nuclear reactor. So that can be pretty fun. I'm in senior design right now, the first part of it. So we're learning about all of the different project proposals that we're getting from industry. So that's kind of a unique thing that nuclear engineering gets to do is our senior design. The last few years, I think maybe the last 3 years or so, the way it's been done is we actually have industrial partners that come in and they pitch a project, and the teams will get assigned to those projects. And so each team kind of has their own project, and it's a real world kind of thing. And oftentimes it's very heavily used by the industrial partner that we have. So those can be really, really interesting. So looking forward to doing that. What else? NE 300 is also a great class. It's kind of, again, the extension of the NE 200 class that Tyler was talking about, which is, NE 200 is very broad overview. NE 300 is all about sort of getting into nuclear physics. It's probably the most, it's definitely the most nuclear physics or atomic or subatomic physics that you would get out of any of the engineering majors. I mean, you're dealing with, the structure of the nucleus and how that actually works, and it can be really, really interesting. And in my opinion, I'm sort of kind of geared towards that kind of thing. So I thought that was really fascinating. Unless you're a physics major, and then you do a little bit more than us, but it's well on its way. So.
Well, and to Jonathan's point, we have students who are more geared towards physics. They either get the physics minor. I often do not advise minors because I think it's more important to focus on what's of interest to the students. But at least taking technical electives in quantum physics or modern physics, those are all things you can do within nuclear engineering undergraduate degree. All right, so I'm going on to the next side here for opportunity. So Jonathan, if you could talk about some of your experiences, because I know you've had some interesting ones.
Yeah. So I've had a few internships now. I'm definitely interested in working for the government in the future. So and I'm sort of also policy minded. Like I'm getting a minor in political science, which is also something very. It's been really interesting and fascinating and very easy to get. So if you guys are interested in that, feel free to like send me a message and I can tell you more about it. But because I've been interested in the policy, especially like non-proliferation related policy, things like arms control, making sure the bad guys don't get nuclear weapons, kind of thing. So I got to do an internship with the State Department, and actually, I was like by far the youngest person there. I got that the fall of my sophomore year. I was in Washington D.C. working downtown every day, at the State Department headquarters, and the reason why I got it was because I had the nuclear engineering background. I was the only engineer there and the youngest person. So nuclear engineering can open a lot of opportunities that you might not expect necessarily, especially when it comes to government and the policy world. That maybe you don't necessarily realize that those opportunities are out there, but they are. And because there aren't that many nuclear engineers, it doesn't take as much to sort of get your way into one of those positions. And that was a really fascinating experience, entirely policy-based, not technical at all, but it set me up for kind of a more technical internship with the Nuclear Regulatory Commission that I did, the summer going into my junior year, so in the last summer. And that was really fascinating. I was doing emergency preparedness kind of work and a lot of regulatory stuff, taking research that had been done and finding ways, okay, this is our new enhanced understanding of emergency preparedness for nuclear power plants, and how can we make regulations that, better fit our enhanced understanding and make better sense in the real world. So I was doing a lot of those things, and that was really fascinating. And an area that I think a lot of people don't realize is there's a ton of planning that goes into, okay, if we're going to build a nuclear power plant or any facility that has nuclear radiological material, we have to plan for what happens if something goes wrong. And there's a lot of thought and a lot of research that goes into that. That's a whole field a lot of people don't realize exists, and it's really, really fascinating.
All right, so the other thing, it's not on here, it might be on the next slide. Now, this goes more into co-ops. So we've had many of our students do co-ops. I don't think either of you have done co-ops, but a lot of times I'll do these with nuclear utilities. It extends the time to graduation, but it's great experience. Can also give some degree of income as well. But it lets you see more of the industrial side of things. Some of our students use this as a stepping stone to work at these companies. I know others who have used this and gone on to graduate school to get PhDs. So it's a very good experience. It can also be challenging to get these internship opportunities. So it's also important to look into opportunities on campus. There is the SURF program, which will pay you to work over the summer with a research group and provide you with professional development opportunities, particularly showing you what it takes to go to graduate school, what the opportunities are if you go to graduate school. Gives you a chance to work with a research group. And when you apply for jobs, a lot of times the jobs will look at that as an equivalent to an internship because you have a lot of the same responsibilities. You have some sort of deliverable that you have to have at the end of your summer. That also leads to the opportunity to work closely with faculty. Because we are a smaller school, we have typically maybe 30. The largest class since I've been here was 45 my first year. So we don't have a large group of students. So the students can get to know the faculty a lot better than in other departments, which makes it easier to approach them for research opportunities. Jonathan, have you done any work with any of the faculty?
Yeah, so I've done research with Dr. Bean, and that's been really, really great so far. Dr. Bean's another one, just like Dr. Garner, who, by the way, from everybody that I've heard this talk to him, and he's absolutely fantastic to work with. And when I had him as a professor, Dr. Garner is great. I'm not just saying that because I need a good grade from him or something, because I don't think I have any classes with him anymore. So Dr. Garner is great to work with if you're at all interested by his research and you're really motivated to get involved in undergraduate research. He's great to work with. Dr. Bean has been great for me because he does a wide variety of topic areas, and he does a lot of the non-proliferation kind of stuff. So I've learned a lot from him with that. He's also heavily involved with the nuclear reactor. So there's been a lot of kind of side projects that I've got to see how a lot of that works. And ultimately, that's sort of what led me to start getting trained for the to become a licensed reactor operator, which is still in the works, but COVID is slowing things down, unfortunately. So
Jonathan, would you be the first student to become licensed? Have we licensed anyone yet?
Yeah, in terms of undergraduate students, so in recent years, yeah, we haven't had any undergraduate students. Myself and a few other students that have been working alongside, we've been training with the senior reactor operator and the reactor supervisor which is Clive Townsend. We've been training with him for the last year and a half or so, but the last 6 months we haven't really done anything because of COVID. But yeah, we would be the first group of undergraduate students to be licensed by the Nuclear Regulatory Commission to operate the reactor since I think the 1970s. So it hasn't happened for a long time. But I know it's something that Dr. Bean, I just had a conversation about him recently, is that he really wants the reactor to be something that undergraduate students have an opportunity to get their hands on and learn about before they get into their senior year and taking the Nuke 305. So I think that's something Clive wants to do as well. So I imagine we see more of that in the future.
I think it's important. And along those lines, remember I talked about my experience in the Navy. Purdue University's reactor, I got here in 2012. It was old, okay? It was constructed in the 60s. A lot of pieces were old. I do vacuum electronics. These were old vacuum tubes, way older than stuff that we do in research. I mean, it was hard to replace them when they broke. So we got a big grant to actually upgrade the reactor. And Purdue is now the first commercially licensed digital instrumentation and control reactor in the country. It's also the largest reactor in Indiana, mainly because it's the only reactor in Indiana. It's 10 kilowatts. So 10 kilowatts, not going to really power many light bulbs either. But the point to what Jonathan was saying is that it's a teaching tool. And from my background, one of the things that I was always somewhat hesitant about as an undergraduate is we didn't really talk about reactor operations. And you can't really teach that to undergraduate students because there's too much other stuff going on. I understand that as a faculty member, but something like what Jonathan is doing is great experience for students with that sort of interest. And it's something that you could use research for credit to do. I mean, 3 credits of research credit counts for technical electives, and it's about 10 hours per week. If you do that a couple of times, and you can count 6 credits for graduation, maybe you do a summer thing, a summer internship or something on campus where you can work on the reactor, you could get licensed. And while a license does not carry to another reactor, okay, licensing on our reactor won't get you a license if you go work at a commercial reactor. But fundamentally, it will teach you how to get a license, which is a very important aspect of that for students who are interested in it. Let's see, more internships, potential for undergraduate students to do research. Tyler, do you want to talk? I know you've done a little bit of research for me. Do you want to talk about your experiences?
Yeah, absolutely. So I've done research for both you and under Dr. Bean. So I took a lot of Jonathan's points that he made earlier. I really do like researching under you. I work with a master's student, Andrew Fairbanks, under Dr. Gardner. Basically, he extends a lot of his research to electronics for at least what I'm doing, and that's very valuable to me because I really like how it sort of ties what I've learned in nuclear engineering to fields outside of nuclear engineering, so it really gives a wide girth to however much you could learn and apply for nuclear engineering. And just like you'd mentioned with Jonathan, I also have been learning and am in the process of becoming a licensed operator for the reactor, which is by far my favorite thing I've done on campus related to research, and I really hope to get licensed as well.
All right.
Yeah, if I could make a tangential point on that, yeah, I guess I was just going to say that I didn't go into nuclear engineering wanting to like do reactor operations. You know, I was kind of in some ways a little bit jaded when it comes to reactor operations because I was like, you know, everybody thinks nuclear engineering is just going and operating a nuclear reactor power plant, which lots of nuclear engineers do that. But I was like, I don't want to do that. I want to do this kind of cool policy stuff that's totally different. But once I started training on the reactor, I realized it is actually, like Tyler made a great point, it is one of the coolest things you could do on campus, like by far. It is absolutely fascinating and really fun. And we have, as Dr. Garner mentioned, you know, the nicest, most new, you know, digital instrumentation and control that is more advanced than anywhere in the country. It's more advanced than, you know, commercial power plant. It's more advanced than any other research reactor because it's all digital instrumentation and control. So it's really cool.
Yeah, I'm a little jaded by that because I did a digital INC change out in 2001 in the Navy, but still, it's very, it's very impressive.
Yeah, fair enough. Fair enough. The Navy's got it beat for sure, but this is pretty good when it comes to the civilian side, I think.
Yeah, it's leaps and bounds beyond what we had before, man. I'll tell you that. And it's great that we have something that's operational. That's the biggest thing. Clubs and organizations, we're getting near the end to leave some time for questions. The American Nuclear Society is our biggest one. We have women in nuclear. My students are involved in the American Physical Society and IEEE. Jonathan, are you involved in, I always get the acronym screwed up, IMMM or whatever?
Yeah, INMM. Yeah, it's the Institute of Nuclear Materials Management. Yeah, yeah, I'm the chapter president this year.
I always get my N's and M's mixed up.
Yeah.
Okay, so there's a lot of opportunities for these sort of involvements to get leadership experience and to meet other people. I'm going through them all very fast. The other one in my area, Fusion Awareness Organization, that one is one that's highly dependent upon student involvement. We have to have a student that's really passionate about that. And I'm also, before COVID hit, I was working with one of my PhD students to start a branch of the IEEE Nuclear and Plasma Science Society here at Purdue. But that kind of got put on the wayside. So finally, we're a small school. You see down at the bottom the nice picture of our department when we had a picnic last year. Hopefully we have a picnic again next year where we all get together. But because we're small, we tend to be more tight-knit than larger departments. Everyone knows everyone. Oftentimes in the larger departments, you might even be in a similar research area and not know other students or faculty. So that's another reason I stayed in nuclear engineering. Fortunately, it's bigger than when I was a student. We only had 6 students in my class. That was barely survivable. Now we're up to around 30. But if you have any questions, please email our student services. This is the email, nuclss@purdue.edu. That'll get you in touch with Holly, who's our academic advisor, and then she can farm the questions out to the appropriate people. You're also welcome to email me directly. You can find my email on the website if you go there. And with that, I'll stop sharing so that they can put up the codes when they need to. And we're open to any questions.
Can you all see the QR code?
Yes.
Yes.
I can see.
Great, thank you.
Something I get asked about a lot if we're waiting on, oh, we got, hold on. Okay. Something I get asked about a lot from FYU students especially is like what kind of internship opportunities. I know I mentioned some of what I got to do, but I don't think we had a chance to talk about it too much. So, you know, what sort of internship opportunities are available? I did mention there are a lot of them in government. Something we didn't talk about are internships with national laboratories. So especially if you're interested in going to grad school, national labs have like a really high concentration of, there are a disproportionate number of opportunities for nuclear engineers at national labs compared to maybe some of the other types of engineers. So if you're a nuclear engineer, getting a national lab spot is going to be, I think, easier than maybe, you know, your run-of-the-mill mechanical engineer. Not to say you couldn't get one there, but if you're interested in doing that, that's something great to look for as well. I wouldn't say most jobs are in government. There certainly are, you know, a lot of government jobs, whether that be on the regulatory side of things, working for the Navy, Department of Defense, national labs, which again, national labs are sort of government, sort of not. There are plenty of opportunities in terms of, you know, working in the industry, whether that be for, you know, a medical isotope production facility. There's a company that was medical isotope production company, you know, that was founded by a Purdue nuclear engineering alum. There's one up in Wisconsin, you know, that's kind of, they're building a facility right now. There's, you know, fuel fabrication facilities you could work at, all kinds of stuff. So I can just keep answering these questions, but feel free to cut me off, Dr. Garner, or Tyler, if you have anything else to add.
The only thing
No, I've been
I'd add
answering
is,
this question.
yeah, so the only thing I'd add to Jonathan's previous answer about the career pool is something that I think is unique about nuclear engineering is it's sort of all over if you want to look. So this past summer, even I interned with Bechtel, which is one of the world's largest private construction companies. Even they have opportunities for nuclear engineers. Right now they're finishing building the nuclear power plants down in Waynesboro, Georgia, and they work with a few of the national labs, a few defense contractors, hire nuclear engineers. They're really all over job opportunities.
Yeah, I don't know the specific information on, we're going to get more questions fashion, I can answer them, but in terms of ratio men to women, I think we're pretty similar to mechanical engineering. I don't know, like I think in my class, there are 7 or 8 girls and we have about 30 in my class, something like that. So yeah, a little bit less than if they're about 25%.
Yeah, I know in my research group, in my research group on the undergraduate side, we have about 60% women. So yeah, I know that from recruiting undergraduates, we tend to have more than on the graduate side.
Let's see.
So just responding to Alexander's question real quick, generally, at least in my experience, nuclear engineering is a lot more of the sort of all-encompassing engineering side of it rather than just nuclear physics, but the program does allow you a good amount of freedom, so you can get a minor in physics, take a lot more physics-geared classes, and that sort of thing.
Yeah, I would say that physics is like nuclear engineering is all about taking what nuclear physicists learned, particularly in like the 20th century during the Manhattan Project and the 50s and 60s, and applying that to real world applications. Obviously, we're taking things that we learned that are more new than that, of course, and things that are older. Like nuclear engineers work on a lot of thermohydraulics kind of stuff that we've been dealing with since the 1800s. So physicists is all about discovering the new phenomena that happens under fringe conditions, whereas nuclear engineers are concerned with bulk conditions and practical applications. I would say that's probably the easiest way to say it. Somebody else asked a question about in terms of the AAE working in like nuclear areas. I know that he's a senior in AAE. He's getting a minor in nuclear engineering. He's interested in working in with like space propulsion. And I know that he did an internship at Idaho National Lab working on the RTGs, radioisotope thermoelectric generators. So,
yeah, I had a chemical engineering student working with me doing microorganism inactivation, and she actually had an internship at Duke doing corrosion stuff for the power plant. So it's very weird that a chemical engineering student doing research for me on something you wouldn't normally think of as nuclear engineering was doing an internship with a nuclear engineering company. On the other side, what the students were talking about with physics, as you move along, the distinction between physics and engineering becomes a lot more nebulous. Things become very gobbled up. The work that my research group does, I have someone who's basically a theoretical physicist. That's a lot of what we do in the group. The difference between what we do and a physicist is our theory is geared towards something more practical, whereas a theoretical physicist in physics will tend to do things that are more very conceptual, very highbrow. Okay? So I consider myself a theorist, but my theory is geared towards actual experiments.
Yeah. Somebody asked a question about how much chemistry is involved with nuclear engineering. I was just going to say really quick, we don't take a lot of chemistry classes. Like I think it might be required to do one of the chemistry classes during your freshman year. I'm not sure you want to ask Holly or Dr. Garner about that. But we don't take a lot of chemistry classes, although chemistry gets woven into our other classes, like particularly our materials class, we handle a lot of chemistry kind of concepts. And like, I'd say a lot of materials ultimately is about, chemistry, especially if you want to get into an area like, developing materials that are going to be in a nuclear reactor and withstanding those harsh conditions. A lot of that is ultimately chemistry. Nuclear waste management, that's a lot of chemistry. So, and David asked a question about how many get. Oh, go ahead.
Sorry. The other thing to keep in mind too is that people don't usually think about it like this, but there is overlap between chemical engineering and nuclear engineering. What we call neutron physics or neutronics is actually fundamental chemical engineering. It's the diffusion of neutrons. Chemical engineers spend a lot of time talking about diffusion. They spend a lot of time talking about thermodynamics. They talk about heat mass transfer. They do they do a lot of the same things we do, just under different contexts. So while I haven't had students do this, there would be the potential for an interested student to take courses through chemical engineering for technical electives, if that's something of interest.
Somebody asked how many students get accepted to nuclear engineering during the transition to major. I would say typically, if you're able to meet the T2M requirements, you don't have too much of a problem getting into nuclear engineering if that's your first choice. Occasionally, there would be somebody that gets out of, that passes out of FYE but doesn't get accepted. I would say that's fairly rare, and that's mostly just because we're a small group of students. With that being said, so like it's not as competitive as like AAE or like ABE or biomedical engineering, but that doesn't mean that it's necessarily an easy major. So don't let that don't let it deceive you too much. It's still very challenging and very rigorous, but a lot of that is mitigated by having a close-knit group of students that work well together and collaborate on a lot of things to help each other get through the classes. So
right, and to Jonathan's point, we have not, since I've been here, had the point where we've had to reject people because we had too many people apply. So if you're interested, apply. If you have questions, please reach out to Holly or me to discuss.
Yeah, somebody asked a question about nuclear engineering. Do nuclear engineers design nuclear power plants? Yes, absolutely. Mechanical engineers are going to work on a lot of the secondary systems, of course. But that's not to say that nuclear engineers couldn't, because we take all of those fundamental mechanical engineering, thermohydraulic classes that Dr. Garner was talking about. Especially here at Purdue, we get a really good basis in thermohydraulics and heat transfer, and thermodynamics. So a lot of the components of a nuclear power plant, nuclear engineers are extremely well suited to work on the design for.
Yeah, but
Yeah,
to Jonathan, to that point, though, a lot of it's going to vary from case to case, and depending on what the given company that's working on it will be looking at. Go ahead, Tyler.
Oh, I was just going to say another big source for jobs in beyond just the design of a nuclear reactor is that non-proliferation side. That would be a fairly large market, making sure everything's safe, up to standards, that sort of thing.
Yeah. Did I miss any questions? If anybody got questions, feel free to copy paste something if we missed it, or go ahead and ask again.
Yeah, I just posted my email to chat. Jonathan, you may want to do that as well. So
Yeah, do that as well.
A lot of good questions. I think we got to most of them.
Yeah, and I'm always happy to answer questions about my experience and that sort of thing. So do not hesitate to reach out to me if you don't feel like, if you're intimidated by Dr. Garner, but he's not very scary. He's very helpful, so don't hesitate to reach out to him too.
And if you have more questions, I'm always available as the academic advisor as well.
Yeah, sort of going along with that, please feel free to contact me. Similar to Jonathan, he said he's getting a minor in political science. I'm getting mine in business economics. So if any of you have any questions about doing other things academically outside of nuclear engineering, please email me.
Yeah, to Christian's question, Dr. Garner answered that. Yeah, it definitely possible. It just depends on what you want to do. But I think Dr. Garner's getting to that.
Oh, let's see here. This question by David is interesting. So at the end of the day, what you do depends on what your interests are, okay? If you really, really want to get deep into the fundamental physics, like if you're interested in quarks and modern physics and all this sort of stuff, you need to be probably a physics major, okay? If you are interested in using physics to do things, then you probably want to be an engineer, okay? That was kind of where I fell. I was interested on the physics side, but when they started talking about quarks and other things, I found it interesting, but I didn't really want to do that. So the work that my research group does is somewhere between physics and electrical engineering, and that weird middle ground falls right in nuclear engineering, because we're kind of physicists, but we're kind of electrical engineers, but not really both. But our application space is nuclear engineering because it falls under fusion and plasma. So I don't know if that answers your question, but it really comes down to what sorts of problems you want to solve. And that will determine whether you wind up an engineer or physicist. But I can tell you that down the line, particularly if you go to graduate school, I've had faculty members that had PhDs in physics, and you would think that they were engineers, and vice versa. My advisor in Michigan, people just assumed he was a physicist, but his degrees were in electrical engineering. So I don't know if that answers your question, but there's more nuance to it than anything else.
Yeah, something sort of tangential to that, and this has just been my experience. Dr. Garner may have a different experience, I don't know. But from the people that I've talked to, I haven't met anybody that did an undergraduate degree in nuclear engineering and then went on to do physics. I don't know why it would be impossible by any means, but I've met several people that have gotten, yeah, I was just gonna say, I've met several people that have gotten undergraduate degrees in physics and then graduate degrees in nuclear engineering. So that seems to be a reasonably common path.
Yeah, it's easier to go from physics to engineer. Physicists will generally look at you weird if you go from engineering to physics, but we did have a student do it. We had a very bright student who got his undergraduate degree at Purdue Nuclear and went to the University of Chicago for physics. So it can be done, but it's much more difficult, to your point. It's easier to do the other way. The other thing I will say is that if you're not sure you want to get a PhD, it's easier to get a job with an undergraduate engineering degree than an undergraduate physics degree. All right. Any other questions? If not, we thank you very much for your time. Feel free to reach out to any of us depending on what your questions are. Programmatic questions or general questions are probably best geared towards Holly or me. I can certainly help a lot with curricular type of questions like major selection, things like that. Like I've already talked about, I've collaborated with people across campus in aerospace, electrical engineering, chemical engineering, ABE. So I kind of have a general feel for what sort of things everyone does based on those collaborations. So feel free to reach out if you have those sort of questions. If you have specific questions about student experiences, Jonathan is a senior, so he's had a little bit more of a broad experience.